Relationship between HCF and LCM of two positive integers. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we explored the methods for calculating the highest common factor, or HCF, and the least common multiple, or LCM, specifically using the prime factorization method. Now, at first glance, these two concepts might appear to be entirely unrelated. After all, one is concerned with finding the largest shared divisor, while the other is focused on finding the smallest shared multiple. However, as we are about to discover in this lesson, there is actually a profound and beautiful mathematical relationship that exists between them, provided we are dealing with two positive integers. Keep this in mind, because this connection is going to make solving complex problems much simpler. The fundamental identity. Now that we've recalled how to find the HCF and LCM individually using prime factorization, let's look at something much more powerful. On this slide, we introduce the fundamental identity. Essentially, for any two positive integers, which we can call a and b, there is a beautiful and consistent rule. The product of their HCF and their LCM is always exactly equal to the product of the two numbers themselves. In mathematical terms, we express this identity as HCF of a and b multiplied by the LCM of a and b equals a multiplied by b. Now, why should you care about this? Well, this identity is an incredibly useful shortcut. Think about it. If a problem provides you with any three of these four values, meaning you know the two numbers and either the HCF or the LCM, you can find that missing fourth value almost instantly. You won't need to go through the tedious process of prime factorization ever again for these types of problems. It turns a complex calculation into a simple piece of arithmetic. Understanding the logic. Now, you might be wondering, why does this identity actually work? It isn't just a magic trick. There is a very logical reason behind it. To understand the logic, let's look back at how we calculate these values and consider the prime factorization of our two numbers. Think about what we learned in our previous lessons. When we find the highest common factor, or HCF, we are looking for the product of the lowest powers of all the common prime factors. On the other hand, when we find the least common multiple, or LCM, we are looking for the product of the highest powers of all the prime factors involved in both numbers. Now, here is the aha moment. When we multiply the HCF and the LCM together, we are essentially combining those lowest powers and highest powers of every single prime factor present in both numbers. If you look closely, this process perfectly reconstructs the original prime factors of both numbers. Therefore, the result of multiplying the HCF and the LCM is identical to simply multiplying the two original numbers, a and b. This is exactly why the formula we saw on the previous slide holds true, and it sets us up perfectly to see how we can apply this step-by-step in the next slide. Step-by-step application of the formula. Now that we understand the mathematical logic behind why this identity works, let's talk about how you can actually use it to solve problems. When you encounter a question where one of these values is missing, you don't need to guess. You just need to follow a consistent, step-by-step process. First, step 1, start by carefully reading the problem to identify your known values. You need to pick out the two numbers, which we call a and b, and see if the HCF is provided. Step 2, once you have your data, write down the formula clearly. You'll write HCF of a and b multiplied by the LCM of a and b equals a multiplied by b. Writing this down first prevents any confusion later on. Step 3, now, substitute the known values into that equation. Replace the letters with the actual numbers given in the problem. Step 4, next, you'll need to rearrange the equation to isolate your unknown variable. Usually, you'll be looking for either the LCM or the HCF, so you'll move the other numbers to the opposite side of the equals sign. And finally, step 5, perform the arithmetic to find your final answer. This usually involves a simple division. If you follow these 5 steps, you'll find that solving these problems becomes much more manageable. In the next few slides, I'm going to show you exactly how this looks in practice with some worked examples. Worked examples. Now that we have understood the theory and the logic behind this identity, let's put it into practice with our first worked example. This is a straightforward numerical calculation to show you how the formula works in a standard exam-style question. Take a look at the problem statement. We are told that the highest common factor of two numbers is 13, and we are also given that the product of these two numbers is 1014. Our goal is to find their least common multiple. To solve this, let's follow the step-by-step method I mentioned in the previous slide. First, we identify our known values. From the problem, we know that HCF equals 13, and the product of our two numbers, which we can call a times b, is 1014. Second, we write down our fundamental identity. HCF of A and B multiplied by the LCM of A and B equals a times b. Third, we substitute our known values into this equation. This gives us 13 multiplied by the LCM equals 1014. Fourth, to find the missing value, we need to isolate the LCM. We do this by dividing both sides of the equation by 13. So, the LCM equals 1014 divided by 13. Finally, we perform the arithmetic. When we divide 1014 by 13, we get 78. So, our final answer is that the LCM of these two numbers is 78. It's a very efficient process, isn't it? We didn't even need to know what the two individual numbers were to find the answer. Now, let's look at how we can apply this same logic to a more practical, real-world scenario in the next slide. Worked examples continued. Now that we have seen how the formula works with simple numbers in our first example, let's move on to our second example, which shows how we can apply this mathematical identity to a real-world scenario. Imagine a technician working on a machine with two interlocking gears. One gear has 24 teeth, and the other has 36 teeth. The technician already knows that the highest common factor of these two numbers is 12. His goal is to find the least common multiple, because the LCM will tell him exactly after how many teeth have passed that both gears will return to their original starting positions. To solve this, we will follow the same step-by-step method we discussed in the previous slide. First, let's identify our given values. We have our first number, A, which is 24, our second number, B, which is 36, and our HCF, which is 12. Next, we apply our fundamental identity. The HCF of A and B multiplied by the LCM of A and B equals a multiplied by B. Now, let's substitute our known values into the equation. This gives us 12 multiplied by the LCM equals 24 multiplied by 36. Before we can find the LCM, we need to simplify the right side of the equation. When we multiply 24 by 36, we get 864. So, our equation now reads, 12 multiplied by the LCM equals 864. To isolate the LCM, we simply divide 864 by 12. Performing that final calculation, we find that the LCM is 72. Therefore, our final answer is that the gears will return to their original starting position after 72 teeth have passed. As we move to the next slide, I want you to pay close attention, because while this formula is powerful, there is a very important trap you must avoid when using it. Common mistakes to avoid. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even when you understand the formula, there are two specific areas where students often stumble. First, let's talk about what I call the three-number trap. Throughout this presentation, we have focused exclusively on the relationship between two numbers. However, a very common mistake is trying to extend this same logic to a set of three or more numbers. Please take note of this warning. If you have three positive integers, let's call them a b and c, the identity where the highest common factor of a b and c multiplied by the least common multiple of a b and c equals the product of a b and c is not generally true. It is vital to remember that this mathematical relationship is strictly limited to exactly 2 positive integers. Do not let this error slip into your work. Second, we need to watch out for simple calculation errors. When you are solving these problems, especially the more complex ones like the gear example we just saw, students often forget to find the product of the 2 numbers first before attempting to divide by the highest common factor. To avoid this, I recommend a disciplined approach. Always ensure you have calculated the product of A and B correctly before you proceed to the final division step. By staying mindful of these 2 points, you will be well prepared for our final summary. Key takeaways. First and foremost, remember the core mathematical relationship we've been working with. The highest common factor of A and B multiplied by the least common multiple of A and B is always equal to the product of A and B. This is the fundamental identity that ties these 2 concepts together. As we saw in our worked examples, the real power of this formula lies in its versatility. It acts like a mathematical bridge, allowing us to find the least common multiple easily if we already know the HCF and the 2 numbers, or even find the HCF if we have the other 3 values. It saves us the extra effort of performing prime factorization every single time. Now, if you're wondering why this works so perfectly, remember what we discussed in our logic slide. It is a direct consequence of how prime factors are distributed. Because the HCF captures the lowest powers of common primes and the LCM captures the highest powers, multiplying them together essentially reconstructs the original product of the 2 numbers. Finally, I want to leave you with one crucial warning to prevent any mistakes in your exams. This identity is strictly limited to a pair of numbers. As we cautioned earlier, please do not attempt to apply this to a set of 3 or more integers, as the relationship does not hold true in those cases. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. Keep practicing these steps, and you'll master this concept in no time. Great job today.